everyone. Thank you so much for joining us. It's 2 after the hour, so I think that we can get started. But welcome to our third and final session of the Electrochemical Impedance Spectroscopy webinar series. My name is Rosie Ray, your host, and I'm an application scientist with NeuroNexus. NeuroNexus is a leading source of advanced electrodes, instrumentation, and software for neuroscience. So much of what we do is grounded in the understanding of EIS, and the high caliber technology of ours would not be possible without the fundamental knowledge of electrochemical impedance spectroscopy. We've had so much fun these past 2 weeks with these sessions. The recordings are available online. I will be dropping a link to those in the chat, so you can go and check those out. We'll be holding all questions until the end, like we've been doing so go ahead and put all of your questions and comments into the question and answer submission, and then we'll be going through those at the end. And then we've also decided, because of everyone's dedication to learning about this topic, we will be issuing an electrochemical impedance spectroscopy certificate to everyone that has been attending this series. So keep an eye out on your email for that. But with that, I would like to thank our co-sponsors, the International Society of Electrochemistry and the Electrochemical Society, for their support in making this series possible. I would also, of course, like to give a special thanks to our distinguished speaker, Professor Mark Orazem, who you will hear more about in just a moment. And now I am happy to introduce the founder and CEO of NeuroNexus, Dr. Daryl Kipke.
Thanks, Rosie. We are pleased to have the opportunity to host and produce this important three-part webinar series. I have the great honor of introducing Mark Orazem. Professor Orazem is a world-renowned expert on electrochemical impedance spectroscopy. He is a distinguished professor of chemical engineering, the William P. and Tracy Cirioli Professor of Chemical Engineering, and Associate Chair for Graduate Studies at the University of Florida. Professor Orazem has received many awards for his outstanding scholarship and is a fellow of the Electrochemical Society, the International Society of Electrochemistry, and the American Association for the Advancement of Science. In addition to his extensive list of research publications, Professor Orazem is the author, along with Bernard Tribollet, of the definitive textbook on impedance spectroscopy, aptly named Electrochemical Impedance Spectroscopy, now in its second edition. Mark, welcome again. We look forward to your talk.
Thank you, Daryl. Okay, welcome back to the third of our and final episode of our series on impedance spectroscopy with application to neural engineering. And let me just go ahead and get started with this. Our co-sponsors, once again, are the Electrochemical Society, the International Society of Electrochemistry, and this is being hosted by NeuroNexus. And this presentation is part of a deliverable from a grant that we have from NIH on engineering the neuronal response to electrical microstimulation. And this grant involves people from Purdue, Florida, Duke, University of Texas at Dallas, and NeuroNexus. So what we did before was we had an introduction on April 1st. On April 8th, we talked about basically how we make the measurements and how we develop models from a simple point of view. And today we'd like to focus on the application to neural engineering. And here, what I'd like to do is to cover a little bit of what we did not cover at the end of the session on last week, and then focus on 2,000 square micron SIROF electrodes in vitro, and then look at 20 square micron SIROF electrodes in vivo, and then look at tinitride electrodes in vitro. So this, basically scanning some of the applications of electrodes for neural stimulation. The image that we use when we sent out the advertisement for the last of the series is an optical photograph of one of the electrodes that we created. This is the third generation, and it had electrodes that are 5 microns in diameter, 10, 15, and 20 microns in diameter. And in addition, there were 2 large pads that we could use kind of as a reference. So what I wanted to cover last week and ran out of time was focus on some of how we use graphical methods to facilitate interpretation of impedance. And so the two issues I want to discuss would be superposition of Nyquist plots and when is the time constant distribution the constant phase element. So last week we talked about, we started out with, building an electrical circuit, and in the process of doing that, we found that if we have the same chemistry, that if you plotted your data in a certain way, the Nyquist plots would superpose. And so I'd like to show you three examples of that. The first one is for reduction of ferricyanide on a platinum rotating disk electrode. So these are different rotation speeds, multiple measurements taken at different rotation speeds. And what we see is that as the rotation speed changes, the impedance changes in magnitude. If we scale this by the real part at the zero frequency limit minus the ohmic resistance, and then for the real axis, we're plotting the real part minus the ohmic resistance. On the imaginary axis, we're plotting the imaginary part divided by the same thing we're using to divide the real part by. And what we see is that all those data that we were showing you on the previous slide superpose very nicely. It's a way of showing you that the chemistry and physics has not changed, just the rotation speed. This is an example from our work on lithium batteries. This one experiment, we over-discharged the battery to 2 volts, and then we waited for 2 days while the battery sort of returned from a very high impedance situation to an impedance situation that looked very similar to what we began with. In this particular case, we decided to scale by the resistance at the end of this capacitive loop. And what we can see is that we were able to superpose those data as well. Again, showing that after an over-discharge excursion, the battery chemistry did not change. What's interesting is that when we did this for the same thing for overcharging the battery, we could never superpose the results, primarily because by overcharging the battery, we destroyed the battery. The third one I'd like to show is for corrosion of magnesium in a saline solution. And what we're seeing here are 3 measurements taken at different points in time. And so about 3 hours separating these 3 scans. And what was done here was to choose this point where the impedance crosses the real axis to be the reference point. And what we see is that when we use that, and you can see that the reference point is here because that number is 1, once again, all those points superpose. Again, showing that what's happening here is that the chemistry was not changing. What was happening as a function of time was effectively the same, but the active area was changing because of the formation of an oxide. The second graphical interpretation thing I wanted to discuss is the question of when is the time constant distribution the constant phase element. And I'm showing you here 2 data sets, one for an oxide on steel and the other is for an oxide on niobium. Oxide on steel was generated by Isabelle Fratteur, and Sandro Caterin was the one who organized who made the measurements for oxide on niobium. And if you don't know what a constant phase element is, it basically is typically used as a way to fit impedance data better, basically. So for example, if we have just an ohmic resistance in series with a capacitance, then we would see a vertical line in a Nyquist plot. But if we have a constant phase element, then this j omega, the imaginary number times frequency, is raised to an exponent alpha. And then we replace the c with a q just to remind us that c and q don't have the same units. But what we're seeing, so this is a constant phase element. If we have a charge transfer resistance, then the constant phase element basically gives rise to a depressed semicircle. Again, we are simply adding an exponent alpha to this. So we're adding one parameter, and it does tend to fit the data better. So the question we're asking, if we go back to these plots, what can we tell from the graphs? And I'm going to argue that I can't tell a thing from looking at these Nyquist plots. The high frequency behavior looks very similar in a Nyquist plot for the oxide on steel as it does for the oxide on niobium. And the situation is not improved if we look at Bode plots. If we look at Bode plots, let me focus on the phase angle. Then at high frequency, what we're seeing is that the phase angle wants to tend towards zero. And the reason for this is that the interfacial impedance becomes very small, and what we're really seeing in the impedance is the ohmic resistance. The ohmic resistance is a resistor, basically, so that means that the current and potential are in phase, and the phase angle would be zero. And for the oxide on niobium, even though we didn't go to such a high frequency, we can see that we're trying to tend toward zero at high frequency. So our solution to that is to use ohmic resistance corrected Bode plots. So the phase angle is the inverse tangent of the imaginary part divided by the real part. So what we'll do here is to subtract from the real part the ohmic resistance. We can do something similar for the magnitude. So if we're looking at the oxide on niobium, what we see in the phase angle plot, which is here, is that we do not really see a constant phase. So this would tell us that oxide on niobium does not have a constant phase element behavior. And in fact, we use a model which is called the Young model, which involves an exponential distribution of resistivity to fit this data. But when we look at the oxide on steel, what we see is that in this frequency range, we see effectively a constant. So we're seeing a constant phase element behavior in this region. What we're seeing also is that at higher frequencies, we're seeing a little bit of a dip. This is something that we very often see when the geometry of the electrode starts to influence the impedance. And we refer to this as the ohmic impedance. And the characteristic frequency corresponding to this dashed line is inversely related to the radius of the disk electrode. We will talk about ohmic impedance more later. So the message from all of this is that models can account rigorously for kinetics and mass transfer, that circuits can provide a framework for model development, and then the models can be expressed in terms of circuits. And graphical methods facilitate interpretation of data. So that was the last little bit I want to talk about last week. So let's talk about application to neural engineering. And again, we're going to talk about sputtered iridium oxide electrodes in vitro. We're going to talk about sputtered iridium oxide electrodes in vivo. And then we're going to talk about titanium nitride electrodes in vitro. So the first ones are relatively large, 2,000 square microns. And this is an image of the surface of the electrode. It is a porous structure. And so if you look at a cross-section, we see that there is a porous layer here. And in fact, a porous electrode model was used to fit this data. And this work was published actually last year in the Journal of Neural Engineering. So our approach is this. We want a philosophy that accounts for both the physics and chemistry of the system and the error structure of the measurement. The data are collected in triplicate, allowing us to assess the stochastic error structure. And the interpretation model accounts for the porous electrode structure and the influence of the iridium oxidation state transitions. There's one thing I want to mention, and this was especially true with the data that we got. All this data came from Stuart Kogan's group. And so if you look at the Nyquist plot, everything looks beautiful, but we're really missing what's happening at high frequency. If we zoom in, we see that there's high frequencies over here. This funny little loop over here, we will eventually discover is related to the ohmic impedance. But we also see these 2 points over here. These points come because of the transition from a steady state behavior to impedance. Normally, we throw away the first measurement we measure because of this transition from a steady state behavior to the impedance behavior. But in this case, we had to throw away these two. Once we did that, we were able to get good fits to these data. Other thing I want to mention is that when we look at the steady state current as a function of applied potential, and the dark circles are open circuit, we see that the current effectively is open circuit the whole time. This represents zero current. So what that's telling us is that we stayed well within the water window. We are not evolving hydrogen, we're not evolving oxygen, and there is the iridium oxidation and reduction, which is a redox reaction that takes place in this system. And what this is telling us is that we've waited long enough, 15 seconds between measurements, to allow that to stabilize. There are 36 spectra. The results suggest that the Faradaic current is not playing a role, and the impedance then suggests that we're seeing really a charging current, not a Faradaic current. Okay, so the approach that we're taking, and I realize that this is going to be a fast look at all of this, and you can look at videos on my website that give you more information if you want to dig into this deeper. We are using the measurement model. This is the program that we provide free of charge. We use this to identify the stochastic error structure. We use this to identify the frequency range that's consistent with the Kramers-Kronig relations. We use this to extract the ohmic resistance and capacitance, and this allows us to identify the frequency that's influenced by the geometry of the electrode. And then we focus on a process model, and this is what we're doing to try to extract physically meaningful parameters. And the key thing I want to emphasize in this presentation is the estimation of the capacitance. Okay, the measurement model is basically a void series, a series of RC elements. If you look, print small, I apologize for that, but we started in 1992 with our first paper on this thing. So we have been working on this for 3 decades, verging on 4. And the beauty of this is that the measurement model, as shown here, satisfies the Kramers-Kronig relations. So if we can fit this model to our data must satisfy the Kramers-Kronig relations too. It is relatively easy to fit, and it will account for different kinds of behaviors, including inductive features. When we use this measurement model and apply it to the replicate data, what we found is that this is the standard deviation of the measurement. The circles are the real, the triangles are the imaginary part, and the blue line here is the fit of a model of this sort to our data. When I first started working on all this stuff, I believed that the error structure was largely due to the potentiostat that you're using. But what I discovered in this work is that a common error structure could not be found. I have theories about this, and we can discuss it later. But basically, what we're saying is that as we change the potential, I think that the equilibrium concentration of the different redox states for the iridium changes. And that gives rise to different error structures. So we had to use a different error structure for every potential. Let me go back. Where am I? One other thing we could do is check for consistency with the Kramers-Kronig relations. In this particular case, we're using a complex fit of our measurement model to the impedance data. And you see that all these normalized residual errors fall within the 95% confidence interval for the fit. That is a way of saying that our data satisfy the Kramers-Kronig relations. Now, if any of you have followed my work, I used to like to say that I like to fit to the imaginary part to predict problems with the Kramers-Kronig relations at low frequency. I found that does not work well for data like this, where we get nowhere near the 0 frequency limit. So when we see data like this, a complex fit is what we need to use. And that's what we use for all the data. Let's talk a little bit about the geometry-induced frequency dispersion. So there's a characteristic frequency that we can calculate that's based on the ohmic resistance and the capacitance. And this capacitance is extracted from the measurement model as a sum, 1 over C is equal to the sum of 1 over the constant capacitances associated with each of the void elements. Now, this capacitance, 1 over C, is actually the sum of the capacitance we want and the inverse of the capacitance we want and the inverse of the capacitance that we don't want, which is the capacitance associated with the geometry of the electrode. So our approach to this problem is to delete high-frequency points. And as we delete high-frequency points, then what we're seeing is that this capacitance contributes less and less, and the overall capacitance becomes larger, causing this characteristic frequency to become smaller. And so we did this. This is showing you the phase angle as a function of frequency. And you're seeing something very similar to what I showed you for the oxide on steel, this little bit of a dip over here. And a characteristic frequency for this data set was around 50 hertz. What we found, and this region over here is the part that's influenced by the ohmic impedance. Yeah, I seem to have lost, it doesn't matter. Anyway, so for each of the measurements, we found a different characteristic frequency, and we used that for that particular measurement to delete points. And this is showing you what the phase angle looks like after we deleted those points. So the proposed model, we have a porous electrode. So with deep pores, then we have to account for the porous electrode model. But we have a distribution of pore sizes, and so the part of the system with shallow pores really starts looking like a rough, flat electrode. So we're having a flat electrode now that is in parallel to the porous electrode. And this model was also proposed by Lazia's group for porous gold electrodes. And we have an ohmic resistance that is in series with all of this. So this equation here represents this impedance. So now let's take a look at what each of these terms are. So for the pore, we have a pore resistance divided by the square root of lambda, okay, we'll worry about lambda in a second, times the hyperbolic cotangent of the square root of lambda. Lambda is a constant divided by an equivalent impedance. And this impedance is the impedance on the pore wall. And this equivalent impedance is the parallel combination of a constant phase element shown here and a Faradaic contribution. And this Faradaic contribution, which I'm showing you here as a series of a resistance and a capacitance, is really due to the iridium oxidation and reduction. And then for the flat part, we have the same thing. We have the same ZF, the Faradaic impedance, and then we have a constant phase element to account for the charging current on the flat surface. I want to tell you a little bit about how we developed that model for the iridium. So if we're looking at iridium oxidation, in the potential range we're working with, we believe that we're really going from 3 plus to 4 plus and back. And so we can describe this as a reaction. The total concentration of 3 plus and 4 plus cannot change. So this is the total concentration. And we can define a gamma, which is the fractional coverage of the 3 plus, the iridium 3 plus, and the total amount of iridium, which would be the sum of 3 plus and 4 plus. We can write a rate expression for the reaction going the forward direction and the reaction going the backward direction, and written here in terms of this gamma. And we need one more equation to solve this problem, which is basically a conservation equation for this fractional coverage gamma. And in the end, we have an expression for the Faradaic impedance that can be expressed in terms of a charge transfer resistance and a capacitance. And the capacitance is not the typical capacitance we expect for like charging of a double layer. It is associated with the rate constants for the reactions. And this work was in that paper that we published in Journal of Neural Engineering. The model fit the data really well. This is okay. To be honest, if I plot the modulus versus frequency, it always looks good. It doesn't matter how bad your model is. Phase angle is a little bit more sensitive. So that's saying that looks really nice in the phase angle. If we look at the normalized residual errors, compare that to the noise level of the measurement, we're seeing that there is some differences. But in fact, these numbers are really quite good. The 0.005 means 0.5% of the value of the impedance. So all of these numbers, the residual errors are with less than that for the imaginary part and less than around 1% for the real part. If we look at the values for the charge transfer resistance for the iridium, we see that it's a function of potential. Capacitance also is a function of potential. And if we look at the RC time constant for the iridium oxidation and reduction, we see that time constant is somewhere on the order of, let's say, between 0.15 seconds to maybe 0.5 seconds. So that's consistent with our observation that when we waited 15 seconds between measurements, we had waited long enough for this reaction to have stabilized. So if we look at the total capacitance as a function of potential, what we're seeing is that that capacitance is on the order of between 40 to, say, I don't know, let's say 100 millifarads per centimeter squared, and it varies with potential. And the percentage of that that's due to the iridium oxidation and reduction ranges from about 25% to about 35%. The last thing I want to show you with this one is to look at cyclic voltammetry. Cyclic voltammetry is commonly used for these kinds of electrodes. So we can get, from this, we can calculate a charge focusing on just the negative current in this voltammogram. And these voltammograms, this one is at 50 millivolts per second, this one is at 50 volts per second. Then the capacitance we get is this Q divided by a delta V, and the delta V has to be corrected by the ohmic resistance. So when we do this, we find that for the slower sweep rate, we get about 70 millifarads per centimeter squared, which is quite on the order of what we're getting from our impedance. And if we look at the faster sweep rate, then we're seeing something that's a little bit smaller. So the idea is that when we're measuring the impedance, we are capturing the low frequency behavior as well as the high frequency behavior. So it makes sense that the slower sweep rate would be more consistent with what we get from impedance. So what we're saying is that our interpretation model is based on proposed reactions and the physical structure. Our observation that the steady state current was equal to 0 suggests that we were well within the water window and that sufficient time was provided to allow equilibration of the iridium oxidation and reduction. And the total capacitance that we obtained, which includes the contributions of the double layer and the iridium oxidation states, agreed with the capacitance extracted from cyclic voltammetry. So I want to focus now on what happens with smaller electrodes, and these are in vivo. And the data were collected in Kevin Otto's group. And this is looking at the G3 electrode again, focusing on the 10 micron diameter, 15 micron, 5 micron, and 20 micron. I want to focus here on the 5 micron diameter electrodes. So we talked on 2 weeks ago about the accuracy contour plot. And here I'm showing you the accuracy contour plot that the Otto group obtained for their system. Out here, we're seeing the potentiostat. They're using AutoLab instrument. So we're seeing the high impedance region where we're making open circuit measurements. And down here, we're seeing the low impedance region where it's a closed circuit measurement. They used alligator clips that were clamped together. If that adds at least a milliohm impedance. So the better thing to do would be to use like banana plugs plugged into a block of copper, like I showed you in the previous slide. But we don't care about that because we're focused on the high impedance part of this system. And this is showing you some of the data we collected for a 5 micron diameter electrode. And what we're seeing is that at high frequency, we are effectively measuring the impedance of the wires. So that means that when we build a model for this, we have to take the capacitance of the wires into account. And that's what we're doing over here. This is the capacitance of the wires, and that is going to be in parallel to everything that we care about. Here is the ohmic resistance. Here we have, this is from our in vitro data. This is basically a CPE that corresponds to the flat surface or the charging current on the electrode surface. This part here is associated with the iridium oxidation and reduction, and this part here is associated with oxygen reduction. We have a kinetic term here, and we have a diffusion term over here. So we can take the parameters we extracted in vitro and plot them on this plot of magnitude versus frequency. And what we're seeing here, the black line here, is what we see for the flat surface. This dashed line here is what we see for the iridium. And this red line here is what we see for the oxygen reduction. So when we're making measurements in vitro, we're using a larger frequency range, and we can begin to see this feature over here, because it's always, when you're looking at things in parallel, it's the smaller impedance that we're seeing. So we were able to capture this impedance of the reaction when we had a larger frequency range. But in vivo, we cannot have such a large frequency range. And so in this particular case, if we say that 1 hertz is a lower frequency, we really cannot capture this behavior. So we end up having the same model, but without the reduction of oxygen as part of the model. It doesn't mean it's not there. It's just that the frequency range we used was not sufficient to allow us to see it. So this is an example of the fit to the data that I showed you in that accuracy contour plot. And you can see that it is really quite a nice fit to the data. And I'm focusing here on the capacitance after implantation. And so we are going to take from this electrode, from the flat surface, we're using the Brugg formula to estimate a value for the capacitance. And this was published in 1984. And basically, this is saying that this constant phase element is due to a surface distribution of time constants. And effectively, we can show that this is going to be the formula that we need to use. Re, this is the ohmic resistance, which is this guy over here. And then we have alpha and Q that we get from this model. The total capacitance then is the sum of this and the capacitance that we get from the iridium oxidation and reduction. Now, what's interesting about this is that these electrodes have been subject to stimulation. The protocol is cathode leading, charge balanced, symmetric biphasic waveform. 1 or more electrode sites in the implanted device were stimulated at the same time. There was 650 millisecond pulse trains with 0.2 millisecond phase duration and 0.04 millisecond intervals in between. I've sort of tried to draw that over here. And then the currents were basically the same for all size electrodes. They were not scaled by the area, and they ranged from 0.015 to 5 microamps currents. So when we calculated the capacitance as a function of time, what we saw was that initially the capacitance was up here on the order of a millifarad per centimeter squared. And then at some point, this is 60 days of elapsed time, the impedance dropped by about an order of magnitude, maybe more than that. And what was interesting is that we saw this only for the 5 micron electrode. When we looked at the 10 micron diameter electrodes, we did not see this. 15 micron, 20 micron diameter electrodes, we did not see this. I think this is it suggests that what we're seeing is an electrode that is eventually damaged by the stimulation current. If we looked at other 5 micron electrodes, what we see is that this behavior is always the same. It works well around 1-2 millifarads per centimeter squared, and then drops by an order of magnitude. The duration, the time it takes to do that, changes, which is probably due partly to the history of the electrode, how many stimulations it has received, and also perhaps variations in the fabrication of the electrodes. So my point here is that the model was informed by in vitro measurements. The data was influenced by the capacitance of the leads, and the capacitance we extracted suggests electrode damage from stimulation currents. So the last thing I want to talk about is tin nitride. And the SEM image of this shows that it is a very rough surface. It is in fact a capacitive material. There is no redox capacity such as what we see with SIROF. A porous electrode behavior was seen. My focus, this is going to be a short part. I just want to focus on a problem I am facing and trying to understand the data that we've collected from this. So from this system, we found 2 models that worked reasonably well. One was very much like what we saw for the SIROF electrode in the first example. One, with a flat surface and then with a porous electrode behavior. But in this particular case, we needed to take into account the capacitance of the leads. But when we fit this model to the data, we did not get a really great fit. And the comparison of fit to data suggests that we need something in series. And so if we put a constant phase element in series, we get a much nicer fit to the data. So if I show this here, sorry, too many equations. But the porous electrode model is very similar to what we showed before. The lambda that we're using is a constant divided by this ZQ, which is which I used as ZEQ before, but this is the impedance on the pore wall, which was shown just simply as a constant phase element behavior. And so for the system, we have an ohmic resistance, we have the parallel combination of these two terms, and then we have an adhesion layer term, which looks very much like this term over here. And then the parasitic capacitance was treated as a pure capacitance. And then the overall impedance is going to be the parallel combination of all of this. Whoops. Let me go back up and this. So if I look at the residual errors with no adhesion layer, we're seeing residual errors that are really quite large. Again, this 0.15 would look like 15% up here. If I look at the model with adhesion layer, what we're seeing is that we are getting a much better quality fit. We're seeing little jumps over here. These are artifacts in the measurement. We cannot do anything about that. But we're seeing that the adhesion layer does give us a much better fit to the data. The capacitance we're getting for the adhesion layer is somewhere on the order of, let's say, 10 and 20 millifarads. And the capacitance we're getting for the total capacitance of the system can get up to about 50 millifarads, depending upon the thickness of these layers and also the area of the electrodes. So the point is that the best fit we got accounts for the electrode surface, the pores, and the adhesion layer. And the capacitance of the adhesion layer is significant. So what this is telling me is that we need to do something to convince ourselves that we really need to account for the adhesion layer for TiN nitride when we never had to account for an adhesion layer for SIROF. So that's the story I want to tell you. That's just, in terms of impedance for neural engineering, I'm trying to show that there's a systematic approach we can use for data analysis. The in vitro measurements are essential because they help guide the model development for the in vivo data. And the impedance guides understanding of electrodes for neural stimulation. So, this is our series. We began with an introduction. I try to talk a little bit about the history of impedance spectroscopy, why impedance spectroscopy is so useful. We then focused on how we make impedance measurements and, for a very simple model, how we develop models for impedance, for interpretation. In this one, we covered a little bit of the graphical analysis that I meant to cover on April 8th, and then we focused on the SIROF electrodes and TiN nitride electrodes. And with this, I want to thank all of you for being here. I want to thank the Electrochemical Society, the International Society of Electrochemistry, and NeuroNexus for their support of this webinar series. Thank you.
Thank you so much, Mark. That was absolutely amazing. Very, very insightful. And so, yes, we can get into some of the questions that people have been asking. So I can start reading those off. And so one person asks, when we collect EIS over the course of a corrosion experiment, we typically fit the same equivalent circuit to every time point, but the interface is physically changing. For example, during active pitting and passivation. Is it justified to use a single circuit model for fitting all of those stages? And are there established frameworks for deriving a time-dependent impedance model directly from the underlying kinetics and transport equations?
Wow, that is a long question. I guess what I would say is a couple of things. One is the Kramers-Kronig relations are your friend. So when you're making, I'm a firm believer in using impedance to monitor things that are changing with time. But you have to realize that your impedance data, especially at low frequency, can be influenced by non-stationary behavior. And so I would argue that when you're making the measurements, find out what frequency range is sufficiently consistent with the Kramers-Kronig relations. All the vendors that sell impedance instrumentation, I think all of them now, provide some way of checking for consistency with the Kramers-Kronig relations. I frankly like mine best, and you're welcome to download our program and use it and see if you like it best too. But anyway, that's one thing. If you have pitting, active pitting, I'm not 100, I worry a bit about there being too many things happening too fast for impedance to be really useful. Do you remember when we talked about impedance measurements, I talked about different timescales for impedance measurements. If the system is changing, such that 5 impedance measurements taken in one after the other look different, but each individual one is consistent with the Kramers-Kronig relations, then we're fine. But if if the system is changing so fast that the measurement at any given frequency is seeing the effect of that change, then impedance is really not going to be a useful tool. And you'll have to look for other experimental techniques.
Very, very informative. The next question, so what features in a Nyquist plot or other EIS plots might indicate that an oxide layer formed or other chemical changes? I understand these interpretations might be different on a case-by-case basis, but I would like to better understand the example you gave.
Okay, let's start with this. Go back to the elephant. Impedance data is not a standalone technique. So if, I showed you data for the SIROF electrodes that looked very similar to data that I showed you for the oxide on steel. And so I cannot just simply look at the Nyquist plots and say, okay, I'm looking at the oxide. The growth of an oxide would be a really fun thing to monitor. And you will see differences in the impedance definitely as that happens. In terms of plots, I like the Nyquist plot as it gives me kind of a visual way to kind of understand what's going on in the system. I really like the ohmic resistance corrected Bode plots. That is really useful to help me understand what's going on in the system. If one of the tricks that I've used to know if I'm seeing an oxide film or not, remember that the constant phase element parameters that we're using by themselves are not very meaningful. What we have to do is to convert them into capacitance, which might be, in fact, a subject for a new webinar sometime. But so what I'd like to do, if you use the Brugg formula, you're assuming that there's a distribution of time constants along the surface. If you use what we call the power law model, you're assuming that there's a distribution of time constants through the depth of the film. And so you can use either one of those things to estimate a capacitance, to calculate the capacitance from the constant phase element parameters. From that capacitance, you can estimate a thickness. So if that thickness is on the ballpark of what you expect, then that would be at least a suggestion that an oxide film is present. But if that thickness is, on the order of, let's say, millimeters, then you know that it cannot be an oxide film, or that your way of extracting capacitance has to be wrong. So I think those are those would be my quick answers to that question. But it's a question that deserves more time.
Yes, and maybe a whole nother webinar would be needed for that. I like that idea. Another question, what is the physical meaning of the units of CPE?
The typical way of explaining a constant phase element, the units come about because you have, the imaginary number times frequency raised to a power. And so the units have to account for that. The CPE itself, back when I was learning impedance, I think we mostly considered it as a fudge factor, just a way to make our data look better. And so it was controversial. It really was. And a lot of people refused to use them just on first principles. But, the fact is that our systems that we're studying are really not ideal. And so the constant phase element comes about from a distribution of time constants. So one option is, and this is the one that the Brugg, from the Sleuters group, Brugg was the first author, in that work, assumed that what we're seeing is the distribution of time constants along the surface of an electrode. So that would be one possible explanation for a constant phase element. We assumed that for the model we developed, that the that the distribution is through a film. And there you were saying that the dielectric constant is fixed because it cannot change too much. So we're seeing a distribution of resistivity of the film. And that seems to work really, really well. It allows us to extract a film thickness that makes sense. It's used commercially for certain systems. So it is, that model is used commercially. There are other approaches that I have used. I will say they're not as well developed, but I'll say this, and this will be something that may be food for thought. At the very beginning, when I talked about model development, I said that we're assuming that we can consider the charging current and the Faradaic current to be uncoupled. And then we build a model for the charging current separately from the model for the Faradaic current. That's not completely true. And what we found was when we accounted for the coupling between the Faradaic and charging current, we saw a depressed semicircle very similar to what we see with a constant phase element behavior. That, we've published that, but I don't feel like we've nailed it. So I feel like we really do understand the surface distribution of time constants and the distribution of time constants through a film pretty well. The coupling of charging and Faradaic current really needs some more work.
Very nice. Another question. Dear Professor, thank you for this excellent series on impedance. I have a question. In a typical impedance measurement setup, to what extent does the use of a Faraday cage enhance the quality of the data obtained?
Beautiful. So the Faraday cage is really essential when the currents are small. So in other words, the wires that you're using can act as antennae and pick up electrical fields from outside. When my student is, so the Faraday cage is there to try to shield you from outside electric fields. And so it really is not so important if you're dealing with low impedance systems where the currents are relatively large. But it becomes very important, for example, for this ultramicroelectrode work that I showed you. So all that work was done in a Faraday cage. And my student, when she is making measurements right now, turns off the lights to try to reduce the effect of fluorescent lights. And she likes to work at night when there aren't so many people in the building because she believes that somebody is doing something in the building that affects the impedance that she's measuring. We haven't nailed that one down either, but she does get beautiful data if she collects it at night. But anyway, so the Faraday cage is excellent. We should do that, but it may not be sufficient if you've got something really heavy machinery in the building.
That's funny. I know a lot of students that have worked at odd hours to try to reduce the noise that they're picking up. There's a lot of superstition involved with it.
Yes, I appreciate her dedication.
Another question, could you please explain in more detail about the Young's model fit instead of the CPE and when it would be used in the shown oxide work? When would you use the Young model compared to the CPE?
I think what I showed you was a way to differentiate. If the ohmic resistance corrected phase angle is a constant, then you clearly have a constant phase element. If the ohmic resistance corrected phase angle is not constant, you don't. Then you have to find something else. I mean, the CPE is, a special case of a distribution of time constants. And so, we use the Young model a lot for valve metals. Young's work was done in the 50s, and if you have access to our textbook, we do cover the Young model as compared to, let's say, the power law model.
Okay. Another question. Thank you for the amazing webinars. I didn't get the actual role of characteristic frequency and its relation to the capacitance. Could you please explore it in more depth?
Okay. So there are a couple of things. I mean, one is, and I remember receiving this question at a conference on impedance. how many time constants are there? And, every physical phenomenon has its own time constant. So the time constant we mentioned was the one associated with charging current, which is 1 over 2 pi times the ohmic resistance times capacitance. And so basically that gives us a clue if we have a non-uniform current distribution as to what frequencies, above that frequency, the geometry of the electrode will be influencing your impedance. But there are other time constants. There's a time constant associated with diffusion. There's a time constant associated with the Faradaic reaction. And so each of these time constants gives us some information about the system.
Very nice. Another person says, hi, great insights. Is there any way we can measure or compare the electrochemically active surface area of the electrodes with complex geometry with EIS?
Well, I think I have to think about this some more. Let me just tell you how I'm thinking about this question. The first thing is that impedance is, in fact, an averaging measurement. So we're measuring a current, we're measuring a potential, and we're looking at the transfer function, the impedance response of the system based on the overall current or total current and potential. There are people who are using local impedance measurements, and that could give rise, that local impedance measurements, basically the one I'm thinking of, uses a probe that has at least 2 electrodes on it, from which you can measure a potential difference from which you get a current. So in other words, you can look at the local current density and compare that to and then calculate impedance based on that local current density. And then you could basically scan that probe along the surface and see how the local impedance changes. I've seen some really cool work done like that. I don't do that in my group, but basically we're saying it's a completely different approach toward impedance spectroscopy. But if you really are interested in the heterogeneity of your surface, that would give you a way to explore that.
Very interesting. Another question is, are you checking the change in oxidation states with some other techniques? Example, XPS for iridium oxidation reduction.
We did not for this work. I think all of that is, that would be great to do.
Another question is, can instrumental artifacts show similar semicircle and capacitive signature Nyquist plots if we take out other factors involved, such as electrodes, electrolytes, in chosen frequency range where the semicircles, capacitive signatures, Nyquist plots is observed if electrodes and electrolytes are present?
Yes. Let me try this. Hold on for a second. Okay, one of my favorite stories. When I first was learning impedance, developing the measurement model stuff, I was really proud of what we were doing. And I was working as consultant for a company that was doing basically different modes of therapeutic drug delivery. And this particular one was transdermal. And so we arranged that I would analyze data from the sponsor. He made measurements on himself. And I guess that's probably not recommended. But most of the measurements I couldn't analyze. He had used the wrong settings and the data was all noise. But there was one set that looked really nice. It looked like this. And I know I'm not plotting, I can't draw very well with, where's my mouse again? I'm putting back. There we go. So this is the imaginary part. And this is the real part. And so I wrote my report and I said, this data satisfies the Kramers-Kronig relations. It's perfect. It satisfies the Kramers-Kronig relations, 2 semicircles. Both are somehow relevant to the system under study. And the response I got was that was a very interesting result because this was his dummy cell. And his dummy cell looked like this, which should show 1 capacitive loop, not 2. And so we finally discovered that he had chosen some kind of a low frequency bias reject setting on the instrument. When we turned that setting off, then the second capacitive loop disappeared. So yeah, other things. If you have like long cables connecting to your instrument, that capacitance of that cable and the resistance will give you a capacitive loop too. So anyway, I'm just saying, yes, that absolutely can happen.
Great. Another question, someone was asking, what is the physical meaning of adhesion capacitor?
What is the physical meaning of
adhesion capacitor? And then a similar question, someone was asking, what do you mean by adhesion layer?
Oh, adhesion. Okay. So when they made this tinitride device, you have a titanium layer, and then the titanium nitride is deposited on top of that. So the adhesion layer is basically what is connecting the electrode of interest, the tinitride, to the rest of the device. And so what I have been pushing to try to come up with a different model to fit this, because I hate the idea of including an adhesion layer in the model. And I present this to you just to let you know that this is not a situation where we know everything. And I do not understand why an adhesion layer might be playing this role. Oxide layers can form on top of titanium. And if that happened during the fabrication, maybe, I don't know. We clearly, we would expect an adhesion layer to be more like an ohmic contact. And in terms of the SIROF, it is. We do not see any evidence of an impedance in series to what we have for SIROF. So if any of you already know about this problem and can tell me what we're doing wrong, I'm happy to hear it. But I think this is a case where the impedance is telling us something, and other work needs to be done to explore whether that really is valid or not.
Very nice. I like the transparency with that one. Another question is, how reliable is EIS for extracting diffusion coefficients of ionic species, particularly in concentrated electrolytes during pitted corrosion? And can it be used to determine concentrated solution theory transport parameters?
That's a good question, and I don't have a good answer for it. My biggest experience working with these kinds of problems is with a rotating disc electrode. And what we were seeing was that I think that the results that we were seeing were affected by the non-uniform current distribution on the electrode surface. So we were getting for the system, the Schmidt number is the parameter we're going after. And the Schmidt number is the kinematic viscosity divided by the diffusivity, and it should have a value on the order of, say, 1100 for the system I was studying. And I was getting numbers like 2000. And so with that particular case, I feel like, no, I'm not getting very reliable diffusion coefficients, but it has to be something to do with the way I'm interpreting the results, not necessarily impedance itself. But I think that it is possible for systems with mass transfer playing a role. The geometry of the electrode, the geometry-induced current distribution can influence the impedance, even at low frequency. And so it may be that that's the issue. I think this is one of those problems that we've been tackling for 30 years, and I don't feel like we've really nailed. There are other kinds of impedance that we can use. If we use electrohydrodynamic impedance, electrohydrodynamic impedance is where you modulate not potential or not current, but you modulate rotation speed at a fixed potential and measure impedance. With that one, we got diffusion coefficients exactly spot on. So the beauty of electrohydrodynamic impedance is that it throws away everything that's not associated with mass transfer, because all you're seeing is the effect of changing rotation speed. That means you're seeing the effect of changing mass transfer. So in that particular case, we were able to get really good numbers.
Very nice.
I did not promise that this is easy.
Okay, I think this is going to be our last question. This is a rather longer one, so I think it'll be a good one to end on. They say in the reference paper, the CV at 50 millivolts per second rate of SIROF electrodes shows a clear peak within the water window. Using the same voltage range with bare iridium, not SIROF electrodes, I observe no peak unless the CV is repeatedly cycled, after which a peak appears. suggesting the presence of a Faradaic reaction. Does this indicate progressive oxidation of the iridium surface during cycling? What are the key modeling differences between bare iridium and SIROF electrodes that explain this behavior? Is bare iridium capacitive? Thank you.
Wow. I don't have enough experience to have confidence in my answer to this question. I know that, again, from conversations of, with Stuart Kogan, that, they see peaks in the cyclic voltammetry that they associate with the oxidation of and reduction of iridium. So a Faradaic reaction taking place, inside the water window, away from oxygen evolution or hydrogen evolution. And from the impedance point of view, we don't focus on that because we're focusing on basically the response to a sinusoidal perturbation at a fixed potential. And so so we're not really cycling, we're not scanning potential, we're just simply focusing at one point and getting a result. So we don't see, I think the two are complementary, and one reason I wanted to show the cyclic voltammetry and to show that we got very similar results is to suggest that the two are complementary. But beyond that, I don't have anything more to add to the answer to that question.
I think that was a pretty thoughtful answer. But yes, that brings us to the end. Thank you so much for everyone that has still hung on. I know we went a little bit over time. Thank you so much, Professor Orazem. This was very insightful. I know that I got a ton out of it. I know that all of our attendees got a ton out of it. There was close to 2,000 people that registered for this and about 700 that attended. And I know that the recordings, which are online, they already have upwards of 900 views. And so I know that this information is really benefiting the people of this field and those in tangential fields. So yes, thank you to everyone. Here are the links for the recordings. They're also on Professor Orazem's website. I dropped the links in the chat, and so you can easily click on that. And then again, like I mentioned at the beginning, we will be sending out a certificate of completion of this webinar series. And so be checking your emails for that. But thank you everyone so much. And yeah, this has been a lot of fun.
Thank you, everyone.